This is the last video for our Unit 8 review. We're going to look at question 11 from the review packet for sequences and series. This question is asking us to write the series in sigma notation. We're going to start with example A here. Remember that in sigma notation, I have to know my starting value for n, my ending value for n, that's how far I need to go, and the formula inside has to be in explicit form. So if my pattern is arithmetic, I need to write my equation in explicit form. Remember, this is the formula you have to memorize, dn plus a sub 0. If it's geometric, we have to write it in geometric form, which is capital A, lowercase a sub n, that's an eraser, a sub n equals the first term times r to the n minus 1 power. So let's go ahead and take a look at what's going on here so I can figure out which explicit form I'm going to use. To get from 9 to 11, I can try adding 2, and it looks like that pattern repeats no matter where I go, which means I'm adding, that automatically is arithmetic, and I have a d value. I'm going to be using this equation to write my formula. So I already know my d value is 2. All I need now is to find a sub 0. I can see that my first term is 9, so if I move backward one stop to make 0, the term that would come before is 7, which means I'm ready to go ahead and write my formula. A sub n is going to be 2n plus 7. So this is my explicit formula. All I need to do now is put it in sigma notation. So here's my sigma, my formula that I just wrote, which is 2n plus 7, and now I just need to find my starting and ending values for n. So we start and find the n values just by counting the terms that I'm adding together. This is the first term, second term, third term, fourth term, and fifth term. So we're going from the first term, n equals 1, all the way up to the fifth term. And that's it for that problem. Let's go ahead and take a look at this other equation. So here's my geometric sequence. This time I haven't actually given you the numbers, I've just given you some of the information. I've given you the first term, I've given you the last term and the last n value. And if we take a look at the formula for a geometric sequence right here, I can see that if I have my last value and my first term and the n value, the only piece of missing information I would need for my equation is the r value. And I can plug all three of these pieces of information into this problem so that I can solve for that r value so I can make my equation. So a sub n is going to be the number 39,366. A sub 1 is the number 2. R is a number I don't know. And n is the number 10. So I've plugged in these three pieces of information, 39,366, 2, and 10, based on the formula that I had up there. Now all I have to do is solve for r. So to solve for r, we can go ahead and simplify this exponent. 10 minus 1 is just the number 9. And we have this r to the 9th power. It's being multiplied by 2. I'm going to go ahead and divide both sides by 2 so that I can get r more alone. So r to the 9th power is going to equal 39,366 divided by 2, which is 19,683. Now the only other thing I have to do to get r alone is to undo the 9th power, which I can do by doing the 9th root on both sides. In the calculator, the 9th root of 19,683 is 3. How beautiful is that? That means that I have all the information I need to make an explicit form function. So any general geometric sequence with this set of conditions would be a sub n equals the first term, which they told me is the number 2, times the r value, which I just discovered is the number 3, to the n minus 1 power. So there's my general equation, which means I can put that in my sigma, and all I have to do after that is find my n values. So 2 times 3 to the n minus 1 power, and we'll go and find our n values. So I always start by counting at the first term, n equals 1, and it looks like I stop this time at the number 10. And we're done.